So good afternoon and welcome to the Maniac Talks. I notice we've got a lot of new people here. My name is Charles Gatebe.
Hello.
I'm the coordinator for this series. Now today I'm very pleased to welcome our speaker, Cynthia Rosenzweig. She's a senior scientist at Goddard Institute for Space Studies. So please, because I know she had to fly all the way from New York to here, so please let's give her a warm welcome to feel at home here. And I'm sure you're flying back after this. Before I invite Cynthia to give her story, I want to tell you a short legend of a young girl who defeated an elephant. It's a teenage girl defeating an elephant. Now, the setting of this story is in Africa, where when people are still living in villages, and most people they are living from the soil. And the villages are surrounded by forest, and some of the forests have these dangerous animals, the elephants, the lions, the leopards, and so forth. So one day, this teenage girl ventures into this forest to fetch firewood, but unfortunately she ended up in the hands of an elephant. Terrified but remaining calm, the girl never assisted as she was lifted by the elephant to its back. So you can imagine this little girl is riding on the back of the elephant. She's very terrified. She fears she could die any time. As they moved through the forest, the girl cleverly started breaking the tree branches and placed them on the back. Then at some point, the girl held onto a tree branch and was able to climb down the tree, and the elephant continues on its way. And she managed to escape the forest. And after she exited the forest, she started shouting for help as she was running towards the village. And the villagers, of course, came towards her. But before long, everybody sees this huge animal, elephant, charging after the girl. And the people became even more agitated. They made a lot of noise. And I think the elephant got scared. It ran away. So the villagers then, of course, carried this young girl on their shoulders, celebrating her escape. So ladies and gentlemen, that's how a little girl became a hero for beating the elephant. Today, one of our heroes is here to talk about her journey. What if and so what? She pioneered the study of climate change on agriculture, inspired by Jim Hansen. All of you, of course, know Jim Hansen. And most recently, she turned her attention to the impact of climate change on cities. Please help me welcome our speaker, Cynthia Rosenzweig.
I'm thrilled to give a Maniac talk here and indeed share the story of my journey in answering this question about climate change impacts. So a lot of the climate change work is on the what if. It's about the climate science, and probably many of you work in that area. But from the beginning, as a trained agronomist, I became very interested in the so what part. Why do we care about climate change? Why, really? It's because it has impacts on the systems and sectors of the Earth system as well as the human systems as well. And so that's what I'm going to share in my story today. So, starting out with my first farms. I grew up in the suburbs of New York City. And basically, when I was about 18 years old, I decided that I never wanted to live in a suburb again. I either wanted to live in the country or I wanted to live in the city. Now, for a long time, I either lived in the country or the city. Now, actually, I live in the country and the city in my computer a lot. But I wanted to share with you my first farms. So, let's see if we can get this. Yes, so here, is in Valle, Italy. So when my husband and I were very young, obviously from this picture, we decided that we wanted to go live in Italy. Not just in Italy, but in Tuscany, which is very well known for Chianti wine, wonderful olive oil, right, etc. And so we set out, and we met actually in college, and we set out and we went to, this is the Google Earth, coming down to a little farm just to the north of Florence on the old road to Bologna. And this was the road to our farm. This was my first farm. And the first day we slept there, the next morning I looked out the window and there was an old man carrying a shovel. And he came to teach us how to till the garden in this farm. And that was the true beginning of my love for agriculture. So, and I'll tell about this one first, and then I'm going to tell you, I made a note of the crops that we worked on commercially. Because one of the things is that agriculture is a mixed human system. It is both a physical system, right, with a physical climate system, it's a biological system, and it is a human system, because farmers have to make money. So to really understand how climate change will affect agriculture, that's why we have to really do interdisciplinary work. But to go to the second farm, so after we lived in Italy for about 2 years, then we decided to come back. And I said, so I had learned a lot about agriculture and growing food in Italy, but I wanted to say I want to learn in the States as well. And so we got our next farm, which is in Thompson Ridge, New York. It's 90 miles north of New York City. Here's the Google Earth picture, here's the road, and this is a picture of our farm. Okay, here's the crops that we grew in both these two places. Of course, tomatoes and vegetables, huge amounts, year-long amounts of all of that. But working with commercial enterprises, in Italy we worked in olives, we worked in grapes, we did vendemmia with some of the Chianti wine producers. We raised chickens, goats, and pigs. We sold them to restaurants. So it's not just, oh, this was fun and you know, we were just doing this for fun. It was actually, we made money on this. In Thompson Ridge, we raised sweet corn for the local supermarket and summer camps nearby. We raised pickling cucumbers for a factory in the Bronx in New York City to make pickles. We raised hay for our sheep, and we had lambs and all of that, and we also shared a herd of beef with the neighbor farmers, and we also raised pigs there. The thing that we made the most money on was Indian corn. Do you know what that is? The decorative corn that's sold in the fall, because it's sold by groups of 3 as opposed to the ton when you're raising like with the corn and the commodities. So these were the first farms. But when also I came back to the States after both of these experiences, I decided that I wanted to study agriculture as a field of study, as a discipline of study. And so I went to Rutgers University, in particular Cook College, which is the land-grant university of New Jersey. And this is a picture of my third farm, which is the Adelphia Research Station at Rutgers, in sort of 2/3 of the way down the state of New Jersey. And here's some of the greenhouses that were still there. So there, I learned how to do randomized field trials. I worked on a special crop, testing a crop probably many of you have never heard of. It's called subterranean clover. It's a Middle Eastern crop. But New Jersey farmers and some of the very new wine producers there wanted to look at this as a cover crop for between the vines. But the Mediterranean climate is very different from the temperate New Jersey climate because it's much colder in the winter. So I did for my master's degree, I did a detailed freezing study on the roots of subclover. And by the way, this is one of my agronomy colleagues, too late, told me there are two things you should never study in agronomy. One is roots, and one is freezing. And I did both. Anyway, but at the same time, we had this in our department, we had the first contact with NASA because, and Steve Unger just came and said hi, but he's off at another meeting. But Steve Unger and Sam Goward, whom I hope many of you know, were, and NASA was engaged at that time with the AgriStars and Lacey project. And so they came to our department and they said, look, we really want to understand what the satellites are seeing and to do work like calibration validation work. And so as a graduate student on the fields here, I did maize canopy radiometer measurements. So this was really my first contact with NASA. So then, at the end of that, they said, our department said, you know what, you really need to hire our graduate student to be with you up in New York City, since GIS is in New York, and that's where Steve and Sam were. And so that's how I got to GIS, those many years ago, and I'm still there. So I wanted to just share some of the people who were my mentors and my inspirers in this journey. So first of all, Sam Goward, who was my first boss, along with Steve Unger. So I'm going to add Steve's picture here too. I also definitely want to acknowledge Piers Sellers as an inspiration, because I don't know how many of you know, but before he was an astronaut, Piers worked on land surface modeling for GCMs, and I did a huge amount of work in that area for the GIS GCM. And so Piers' model, which was called the Simple Biosphere Model, was always so good and so great, and he was always doing such a fantastic job with it. And we were having a hard time with ours, and I was always going, we have to keep going because Piers is doing such a great job with the Simple Biosphere Model. So he was definitely one of my inspirations. I don't know how many of you know David Rind, but David Rind really taught me everything about climate. He's just absolutely a fantastic scientist. And even though he's now emeritus, he is still helping he's helping Gavin Schmidt and all the modelers at GIS help the model still be the best it can be, the GIS climate model. So David is a very, very close colleague at GIS. And then finally, of course, Jim Hansen, the director of GIS, who is the director basically almost the whole time I've been there, except for just now. Gavin is there for the last 2 or 3 years. But when I was a lowly graduate student, since I was the graduate student that they said, eventually came, that they embedded, right, at the agronomy graduate student embedded at GIS, that was the time when the GIS global climate model was used for the very early high CO2 runs and simulations, and it was called, at that time, the way they were done was doubled CO2, right? So I don't know how many of you know, but Jim Hansen is from Iowa. So this question, so Jim is on the 7th floor. I am like on the 2nd floor, like on the air shaft as the graduate student, very lowly graduate student. This question comes filtering down from Jim. And the question is, with these doubled CO2 runs, which were showing significant changes in climate caused by the increases in greenhouse gases, the question came down, filtered down from Jim. What will happen to food? So I've just been incredibly fortunate because really I was the only one at GIS who could really begin to answer that question, since I was the only one with agronomic training. And so I'm now going to share with you the work that I've done, starting from the beginning and it's a telescoped version. It's about 10 papers that we worked on to answer this question. Okay, so here's the first one. This was my first ever peer-reviewed journal article. It was published in 1985, Climatic Change. That's Steve Schneider's. Those of you who know also Steve Schneider, very, very, very wonderful climate scientist who has since passed away. And so the first question that, so learning about the model, how it's making the projections. Okay, so how can I begin to answer this question? So the first thing I did was I looked at how changing climate will affect the regions where crops are grown, right? Because there are different crops in Mediterranean regions and in northern regions and in arid regions, et cetera, in different climate zones. So a changing climate will mean that the zones where crops are grown can change. So what I did was I created an expert system that included the environmental requirements for the growth of winter, spring, and fall sown spring wheats, because there are different kinds of wheat, and I specified them for North America. And then I had that expert system. They need this many growing degree days. They need this minimum temperature. They need, in order to vernalize, for example, and they need this much precipitation. And so then, having that set of expert system, I then ran that through with the simulations of the control run and the double CO2 runs. And so this was a projection of, these are the actual ones, a map. These are translated onto the very large grid size, 8 degrees by 10 degrees, which is what the model was run on at that time. Right? This is the control run, which is matching somewhat okay. As always, models are not perfect. And then this is the answer of the double CO2 run. And what we see is the potential for expansion. So what the model showed, and what this system showed, was that because of the warming, that the areas of wheat in North America, primarily in Canada, would expand. There were other changes, though, that were very important, having to do with these differences in the winter, spring, and fall sown spring wheat, because there are different qualities of wheat. In order to get very good bread wheat, you have to use the winter wheat. The spring wheat and the fall sown spring wheats they're producing soft wheat, of much more like used for macaroni and pasta, things like that. So you see that right away, it's not only, the regions would change, but also the quality of the crops would change. Okay, that was the first step. But what I realized very early on was that just changing the regions is not it's important. It's very important where crops are grown, but the number one thing that we need to know about agriculture, this is expanding, but a very, very important thing that we need to know is yield. What is going to be, this links up to the commercial part of it. Remember that it's an economic sector. So I realized that we needed another tool, not just these environmental requirements of where the crops would grow. And so what I did was I went around the American Society of Agronomy, and I found the colleagues who were doing crop modeling. And this is wonderful colleagues, Joe Ritchie, Jim Jones. Some of these are the premier crop modelers of the country. And I engaged them and worked with them to utilize the models to make projections of how the yield would change. And one of the reasons, what the models do is, so you can see, and it's all the satellites are so great because it's saying what's happening in the surface, right? And of course now we're in the satellites with soil moisture and SNAP and everything. We're getting down into the soil. But what the crop models are doing is it's modeling all of the whole part of the crop through its phenological, its growth stages through the season. How does it react to climate, to weather every day? And they run on daily inputs. And so what you're actually then getting is you're growing the crop in your computer in different climates. So I wrote Jim a memo and I said, in order to really answer your question, we have to use crop models. So I then set out to use this family of models. But guess what? We had to modify them because there are two things, because it's not only the climate that's changing, but the carbon dioxide is changing. And we all know from 5th grade biology that CO2 is necessary for photosynthesis, right? And when you have more CO2 in the atmosphere, there's more photosynthesis in the crops. It depends if you're C3 or C4, et cetera, et cetera. But we had to modify the models to add in the CO2 effects to be able to really predict how the yield would change. So what this is, I found this, getting ready for this talk. This is the actual, I think, the first description of how we modified the models in terms of what we did for the routines on photosynthesis. And CO2 has another very, very important effect on the crops. You know how the crops have stomates on their leaves that open to have the CO2, be able to have the CO2 come in. Well, when there's more CO2, the stomates don't have to open as much, and you get higher stomatal resistance. And this then affects the evapotranspiration. So this part is what we did for the photosynthesis, and this part it follows on for a couple of pages, is how we modified the models to take photosynthesis into account. So then, rather than remember those, we were doing things on big grid boxes. Now we're still doing things on big grid boxes, but now what I started doing really was specifying sites with the soils and with the planting dates, and getting much more realistic about growing crops, representing in models the growth of crops actually in fields. And then what we would do is, in order to get up to the grid box, we would use soil databases from the Soil Conservation Service of what are the dominant agricultural soils in those grid boxes. So these were the sites that these are climate stations that we use, and this is some of the early results, which are the series wheat. That's the model that we started out with, and this is for Amarillo, Texas. And one thing that's interesting here is, so the dark lines are the base run, and then the dot is the GIST 2 times CO2, and then the lighter line is the GFDL model. I like this. When I looked back, I said, phew, we were using more than one model. Because if you only use one model, you start to believe it. And it's not scientific. Right? So I felt very good that even from the very first, even though, of course, I love the GIST model, and it is the best model, but we were always checking it and making sure and having model-based uncertainty in what we did. And also we were looking at dry land and irrigated settings in water is a hugely important factor in agricultural production, and we also looked at that in the beginning as well. So this is the EPA was asked by Congress to actually do the first national assessment of climate change. We're now getting ready to do the 4th national climate assessment. And so I helped to organize not only the Great Plains part, but I helped to organize crop modeling across the whole country. I was asked to do that. And that's what's in this volume. Okay, so what's still missing? Economics. Because you can't really get the answer of what would happen to farmers unless you look to see, well, what would happen to their prices and their income. So as part of the national assessment, I then enlisted a wonderful team of economists led by Rich Adams from Oregon State. And so really then he and I really did the first, in the United States, work on bringing together the climatic part, the biophysical part, and the socioeconomic part. So these are the crop model results. I won't go all over that, except just to say, it's hard to see, but this is the wheat results, this is the soybean results and this is the corn. So we started expanding the numbers of crops that we were modeling. And then these were the results which were published in Nature in 1990 of some of the economic results. And it's actually also very instructive when you look at the results of the prices. I hope people in the back can see it. With the GIFS model, the prices went down. With the GFDL model, the prices went up. So, this is also really, it's good. We can't get too, enamored of, we're really looking about what trying to understand. The models are tools. The models are tools for understanding, for thinking through these processes. So that's the inclusion of the economics. Okay, so I threw this slide in, put this slide in to show that in 1988, it's a very famous year for climate change because that's when Jim Hansen testified to the Senate Committee on Energy. But the point I want to make to you today is look at what else was happening in 1988. The Committee on Agriculture, Nutrition, and Forestry of the Senate convened a hearing on the potential effects of climate change on agriculture and forestry. And so you see, it's not as if people were doing climate and climate and climate for like 25 years, and then all of a sudden they thought, oh no, what's happening to impacts? The impacts question, that what if and so what question, that came from the very beginning, because this is also in 1988. So it was really an honor and a privilege to testify at this hearing based on the results that I showed in the previous slides on the U.S. National Assessment. And this was focusing on the U.S., right? But when you think about it, when we think about our whole agricultural sector in the United States, it's not just what happens in the United States that affects our growers, right, and our producers. It is what happens elsewhere. So very early on, the focus also expanded, not just from the U.S., but to what would be happening in the rest of the world as well, to world foods, and so to see what would happen to food production and food supply elsewhere. So we found this, it's a scan of a symposium on the implications for development and financing, but it was on impact of climate change on what was then called the third world. We don't call it the third world anymore, we call it developing countries. But look, Jim was there, Bob Watson was there, and so you see everyone was really sharing what these early results were showing and thinking about what are the implications. So this led to doing the same thing that we had done for the United States, but for the world. And so this work was published in 1994 in Nature, and Martin Parry, who is a British geographer, he was the co-chair of the IPCC Working Group 2 of the fourth assessment. So basically, everything that we did before that I was sharing, that same methodologies, we then used here. Here we're showing GIS, GFDL. We've added a third model, UKMO. All the project people would call it the UKMO models. That's from the UK, right? So we're still doing climate model uncertainty, which is very important. We're also showing the uncertainty in the CO2 effects. The CO2 effects are very, very hard to estimate because it's really hard for experimental work which shows these increases in the photosynthesis and also help on the water use to really be extrapolated to field scale and region scale. Are these results, which are done from my agronomist colleagues who are great at growing crops, but are they really going to be manifested in farmers' fields as we go on. That is actually yet to be proved observationally. So that's why we always do just without CO2, in which there's very dire projections. But when you keep those positive beneficial effects into the simulation, it's very much a mixed story. So the major result of this work is the bottom bottom paragraph here, and this is what it is. It's that when you look at these results, you see that at higher latitudes, the results are either more neutral or even positive, because those crops are not stressed by high temperature nor by water. But in the lower latitudes here, we're seeing this was Eucama was the strongest, but let's say here and here, the lower latitudes had the more negative effects. Which countries, which types of countries are in the lower latitudes? Developing countries. And so this is really one of the major results, not just from this study, but this was really one of the first studies that actually brought this forward so clearly. But this was taken up by the IPCC, and this is really one of the major results that the IPCC, now moving into its 6th assessment, has come forward about the impacts of climate change. That the developing countries, and it's in other sectors besides, but it's very fundamentally in the food sector. So just to give, I think I'm going to do 2 more right on this kind of modeling and climate, and then I'm going to shift gears a bit. So I want to also highlight, so one of the things that we then want to do, okay, so we did all this modeling, projections, assessments, right? But we need to understand it. So with a wonderful mentor, Daniel Hillel, who said, look, we've got to delve into this more. We have to understand it. How does it compare? How do these results compare to things that have happened in the past? So with Dan, we did a study on comparing the projections coming from the global climate models to the climate and the effects of the Dust Bowl. Here's the Parma Drought Severity Index in 1934. And what we found was that the Dust Bowl may be characterized as a preliminary analog, but that the higher projections coming from the GCMs produced even more climatic consequences than the Dust Bowl. And when we look at some of the droughts that have been occurring in this country and in others, this was in '93. We're considerably past that now. We see that we appear to be on a trajectory in which the severity of the droughts in particular is growing. And then I just want to share that then Daniel went on to win the World Food Prize, and in part for his work on climate change, and his us out in the field and him doing early water studies in Israel. Let's see, where am I? Good. Okay. So this was all, climate change, 2030s, 2050s, 2080s. Wait a minute, what's happening right now? So in 1997 and 98, we had really big El Nino events. And we said, again, we can't just always be just doing these kinds of assessments and models. We have to really work and see what's happening now on shorter time frames. So with a NASA IDS project that included Jim Tucker and Asaf Anyamba, we did a big study. We brought together oceanographers, Tony Busalaki was part of it, and the global climate modelers and the ag modelers, et cetera, and the remote sensors. And we really worked on understanding the role of the major modes of variability as the trends of climate are marching forward. But of course, these systems of the major modes of variability are operative as well. So we tackled that. It's actually quite a challenging project. but with a great young woman researcher, Annette Wanabo, and with data from Jim and Asaf, we did a classification of ENSO years using, and then we did VCI for the Corn Belt, and showed that it's really, but El Nino, there wasn't that much of a signal, but the La Nina signals actually there wasn't a La Nina signal in the Corn Belt. Okay, all right, we're taking a break from modeling. I came to feel, there's modeling in the future, but I came to feel that for working group 2, which is on impacts, adaptation, and vulnerability, we could not only have a science that did a very good science, but the science in the mode of projection or this kind of climate analysis. What we needed to do was look at there were already, based on the great, for example, the great GISS temperature data set, that most places in the world were already warming. So what's the impact question? If the world is warming, what are the impacts? Have there been any impacts yet, right? So I said to the IPCC folks, look, we've got to tackle this in working group 2. And so this is chapter 1 of the 4th assessment report, and it is an assessment of observed, not modeled, observed changes and responses in natural and managed systems. So this is an example. So here are time of first appearance of 4 insect species in Spain, right? These are pests and diseases of potatoes. So look, in each one of these, this is over this observed period when it has been warming, right? Especially from about like the end of the 1970s when there really was the big shift in the warming. All of these were appearing earlier. All of the pests were appearing earlier because it was getting warming earlier. And this is a documented, observed impact, not modeled. So what we did in the IPCC, and it was in, this is from working group 2, A4, and then it was in the synthesis report, we put together an enormous database it had 28,000 entry points of observed changes. And we then set out to ask an even tougher question. So we definitely found that significant changes in physical and biological systems are occurring on all continents and in most oceans. This, by the way, is the Nature paper that came out of the IPCC work, of available data in Europe and North America. But then we asked another question. Can those changes in impacts be attributed to anthropogenic climate change? This is a big deal in the climate science side, detection and attribution. So what we did was we asked the detection and attribution question on the impact side as well. And the way we did it was we had our database of observed changes, we had the gridded temperature changes, and we calculated the probability of significant change occurring in both data sets. Now, one more thing, very important. What these boxes are showing, this is physical systems, this is biological systems. This is the number of significant observed changes. This is the number of significant changes consistent with warming. Because there's a lot of, in the newspaper, you get a lot of, right, there's a lot of, this is changing, that's changing, this is changing. But wait a minute, how do we know that those changes are related, first of all, to climate? And so we went through every single one of the databases and every single entry. And the very first thing we had to do was see whether the change was consistent with warming or not. So for example, what could cause changes that had nothing to do perhaps with warming? Like land use change, air pollution, Anna's here, right? Yeah, there can be things that are not climate related. So we tried to be very rigorous in doing this so that we could then make the attribution statement that anthropogenic climate change is having the significant effect. Okay, back to models. So I did that for a long time. That was a huge amount of work. But I always, of course, said, look, we have to keep on and we have to improve how we're doing the modeling for projections of agriculture. So in 2008, we were at it was a water conference, water management conference in Florida, at the University of Florida, and Jim Jones is a very, very good colleague there. And and there were lots of modelers there, and also Mark Kane was there, a wonderful climate scientist. And at the coffee break, I said, look, we've got to come together, and we have to seriously work together to improve the scientific rigor of the modeling that we're doing. And so that's when AgMIP was born. And some of you may be familiar with CMIP, which stands for the Climate Model Intercomparison Project. They are the ones who make all the projections, multi-model projections, that the IPCC uses, and also the whole world, UNFCCC, UN Framework Convention on Climate Change, the whole world uses those projections. So the goal of AgMIP is to have those projections be done with the same rigor, but for what will happen to food. And so this is the example, this is one example from AgMIP, in which we thought that there would be 5 to 10 wheat models coming out of the woodwork. 27 came out of the woodwork, and we're now even up to 30 or so. And everything is protocol-based to do very rigorous intercomparison across the models. And this is some of the first results that came out with very detailed experiments, field experiment. Remember back to the randomized field trials from the very beginning. They're in 4 different, very highly different environmental settings. And the X's are the observed, and the two box and whiskers are, one is when the modelers don't have very much data, that we only in the protocols gave them just like the beginning and the end of the season or something like that, just very little data, so that they couldn't tune their models to get the right answer. And then we gave them a full set of the data from the field experiment, and that's why these error bars are shorter. But the important thing in this, so first of all, that's very important, because in a lot of the world, that's all we have. We don't have a lot of data. So it was but it was important because in both settings, if you look at the median lines compared to the observed, the multi-model ensemble, the median of the multi-model ensemble did a good job. And this is very similar to what the climate models found when they went to the multi-model approach as well. So the ensemble mean replicated observations better than the individual models. This allows us in our protocols to identify why are there disagreements so people can improve their models. And we're doing this in AgMIP in wheat, not only in wheat, but rice, maize, sugarcane, grasslands, bioenergy, et cetera. So that's a big part of what AgMIP does. But then we do as well, using those modeled improvement, but having the models then run on grids. This is like for IPCC. We're very proud of this. This was in the IPCC. This was cited in the IPCC 85. This is the median of 7. GGCM stands for Global Gridded Crop Models, 5 global climate models. And for the very first time, it's a little bit hard to see, but there are hatch marks where the models agree. And this makes it like CMIP. And this makes these projections more rigorous than basically have ever been done before. So we're really, really, really proud of it. And it's not that the results are very different. Remember, we talked about the lower latitudes, more vulnerable to climate change. We're still seeing that. But it's that this time, when we present this for use in to the policymakers, for whatever they decide, it is much more rigorously developed. So, what are we doing now? We're now beginning AR6. And we feel in AgMIP, we now have building blocks that can now allow, again, something new. It's like the next advance. And this is that we have our regional research. Remember back down there in the Great Plains, we were looking at the regions. We do this now at farming system level with crops, livestock, and socioeconomic modeling. That's here as well. And we also have the global gridded models that I just showed you the results of. And don't forget the economists. We still bring them on to work on what will happen to prices. This is a little bit blocked off, but what this is showing is that the prices across 10 global economic models with projections of climate change and the effects on crops are with great uncertainty, but are all projected to increase. So we are, based on an Aspen Global Change Institute, we are embarking on the IPCC special report on 1.5 degrees C, an assessment that is coordinated across the globe and the global and regional scales. Mostly the ag work has been done, well, there's the global gridded, but what's that? How is that really representing what's going on in those grid boxes? Then we have many, many great studies, but they're just at these small areas, and it's like, I say it's like beyond apples and oranges, it's like a whole cornucopia. We can't ever compare. But with now that we have the building blocks in place, and we have the models and the modelers working together in protocol-based work, we think that this is going to be the next advance for not only the 1.5 degrees C, but also for all we hope contribute to AR6. So I just want to point out one thing here. So you see, now that we have all this in place, we can look at extreme events and shocks, both much more near-term sustainable development. We have risk and resilience, adaptation and mitigation, and food policy. But this is the part I want to highlight. We now are bringing in a new group beyond the economists, and they are the nutrition scientists. Because we all know it's not just yield, and it is not just calories anymore. And so it's very, very, very exciting because we're really now coming together to bring, we think, also, I really like this, we hope, provide the information that's really going to be, that's needed so that the agriculture food system, it's not just delivering calories, but it is delivering, and yield that I talked about in the beginning, but it's delivering health. And that's what we're working with them on now. Okay, coming back to Goddard, we're almost done. Exploring links between, so we're with Dahlia and all these folks here, John Bolton and Krista and Joanna. Sibri is in Africa. Joshua Elliott with us, George Huffman here. What we really want to do now is come back to the remote sensing and really see with these great products that are all going on down here, fantastic. How can we really link them with the crop model ensembles to be, then it's not just like a home run, it's like grand slam home run. So that's one thing that we're engaged in those conversations now. And I'm just giving one example, which is that this is the work of Jasmeet Judge from University of Florida. She's on the SNAP team. And this is the kind of thing that can be done, again, not just in looking to the future, but within season, because that's where the near-term measurements really can help. With assimilation of the remote sensing products, linked to the crop growth model, estimating that root zone soil moisture, and then creating decision support systems. So this is the kinds of applications that we're exploring right now. I think that's the end of the crop part. I promised at the end just a few words on cities, because I believe that we need to work on climate change wherever we are. And GIS is in Manhattan, New York City. We are in New York City. So we were asked to work with the government of New York City, actually starting back, it started in 2008. And so with others, with GIS scientists and others from around New York City, we work with the city to provide the knowledge base for climate resiliency And this, for example, we work with sea level rise specialists to make projections that are downscaled, that are specific to New York City with climate change. So we were all doing that, and had published a report in 2010. And then at the end of 2012, Hurricane Sandy happened here. And literally, or figuratively, the city called us the next day and said, we need you to work with us again. And so we led the technical team that developed the climate projections that are used and are still being used, that have been and are being used, not just asking this question, they're still being used in the rebuilding efforts in New York City. And that program is $20 billion. And it is sometimes I call it the tipping point. You know, in climate science, we have a whole thing about tipping points, you know, like the melting of the ice sheets and the rate of change reaching a time when it gets much faster. This incorporation of climate risks due to climate change in the rebuilding of New York City after Hurricane Sandy, I believe, is a tipping point, not just for New York, but for the US, for resiliency to climate change. It's acknowledging explicitly the risks of climate change that all the cities and all coastal cities are facing. So from the beginning, when we did the work in New York, you know, we're NASA and we're global, and so at the same time we started a network of urban climate change researchers, and it's called UCCRN, Urban Climate Change Research Network. And what we have done is we created for city decision makers the knowledge that they need, because the IPCC is really focused on the nation states. It's really focused on the countries. The cities need their own. It's so much information about the urban energy systems, urban health, the climate projections, air pollution, the interactions. So we have to get in to work with us on this. So we did the first one, was published in 2011. This one is in press now at Cambridge University Press. And then this is one final Goddard connection here, is we have regional hubs, so that this has to do with the whole dissemination and outreach. So we have regional hubs for this, and one of our hubs in Latin America is in Rio. And so there's now, with Dalia, we're working on, there's now a NASA Rio partnership, and we're working with Rio to work on how they do sea level rise projections, how we do them, bringing the two together. And they want us to have, we're going to do that before the Olympics, so that we will say that the NASA partnership is really in place. I'm sure other things are going on as well. I think this is the final science side, because it builds on the New York work, and this brings it also back to NASA, not just Goddard Space Flight Center, but all of NASA's centers. So Olga Dominguez, when she was the assistant administrator for the Office of Strategic Infrastructure at NASA headquarters, she learned about what we were doing and how we were working with New York City. And she asked us to help put together for NASA a Climate Adaptation Science Investigators Work Group. It's called CASI. And there are CASI scientists at all of the NASA centers. And it was founded not just as a science group, but in direct partnership with the facilities managers. I'm not sure if, and Mark is here, and Mark is not here in the room, but Mark Carroll is the Goddard PI. So what we are doing is really we're working so that NASA has an agency-wide effort to build climate resilience, and I think it's one of the few programs at NASA in which the NASA scientists and the people who run the facilities, who make it all and keep it all working for the missions, are coming together. So it's very exciting. And we've had 6 workshops at centers around the country in which we bring together the facilities folks who manage the missions, but also the human resources, because when it's hot, people can't work as much, and also the environmental managers, because NASA manages a lot of environmental systems as well. And we provide the projections, and so this is happening. And this was based on the New York work, but it really was bringing the New York work to NASA at the NASA centers. And I think that's the last science one. And I just want to say thank you to my family.
Yeah, so we have time for a few questions and comments.
Please say who you are.
Oh, I'm Joe Whitty, and I'm curious why you're picking 1.5 degrees C as opposed to 2.
Oh, I will certainly tell you that, and it's actually a huge discussion among the scientists. It does not come from the scientists. It comes from the negotiators at the UN Framework Convention on Climate Change. In the preamble of the Paris Agreement, which was signed in December, it says the ambition is, it says we're going to agree to all aim to 2 degrees with the ambition for 1.5. And the UN Framework Convention on Climate Change then issued a special invitation to the IPCC. Actually, Jack Kay was just up at GISS, and we were discussing this with Gavin, because on the impact side, the difference between 2 and 1.5, it's really scientifically actually very hard to characterize those differences. Right, that's on the impacts and resilience side. But in AgMIP, we do a lot on the mitigation side. We have partners who do the mitigation side as well. And if indeed the countries of the world, right, agree that we have to mitigate and go down to 1.5 instead of 2, agriculture is going to be called on to be much more active in mitigation. I didn't talk about the mitigation side here, but after the energy sector, agriculture is the largest sector that produces greenhouse gases. So what in our design of our 1.5 assessment, and we're all meeting actually in France next week to I hope decide the protocols. It's really then on the mitigation side. What will be the effects of and then we also have to bring in the land use side on the agroforestry and the forestry side. So it's very challenging, but that's the answer. It didn't come from the scientists.
And you touched on it just now a little bit, but with regards to forestry, is there any accounting for forestry in so you said, for example, that Canada was going to have better, more productive croplands. How is that going to compete with increased timber production?
Yes, so it's really in the AgMIP system right now, that is handled, believe it or not, more in the economic models than it is in the biophysical models. What we want to do, and I'm hoping next week we're going to make progress on this, is to really bring the agroforestry and land use change modelers together with the AgMIP biophysical modelers. But right now, a lot of it has to do with the economics of it. Which system is more economical? And in the way the models are formulated, that then determines the expansion of agricultural crops. Shifts in comparative advantage in different regions of the world, and then so if it gets cheaper to grow a crop in a new location, those models are going to then respond by expanding agricultural land there. So that's where we're getting that now. But it's a great question, because that's where one of the areas where we're going.
Who is studying the predators of the insects? When do you bring that particular model into this model?
Yes, great question. Because everybody knows, I'll tell you something, this is something I often say. There's been more hand-waving about pests and diseases in agriculture and climate change than anything else, because it is so hard to study, and that's what your question illustrates. Because it's an ecosystem, It's not just those pests. And in order to do that, then there's a whole group of entomology modelers who are doing that. But it is really hard to really project how ecosystems, right, those, is it, which one is, what's going to happen to the food stock, what's going to happen to those critters, what's going to happen to their predators and prey. So, there are entomologists who are working on that, but it's tough.
I'm Amber Emery, and I'm a radar research meteorologist here. So this is a really nice talk, and I haven't thought about climate change and food that much, nowhere obviously. So my question is, what kind of assumptions go into the model about water use? So I'm thinking about things like I did my PhD at Texas Tech there, and they're just
Great school.
pumping the Ogallala, aquifer there,
Right.
Or in the Southwest where there's going to be, at least the climate models are showing that there's going to be greater amounts of heat and drought there, and also, do you look at the frequency of precipitation? So that's kind of my question coming from the
Yes. So the answer on all the regular climate variables coming from GCMs, that's the precipitation, also the intensity, the rate of it, how that changes, that part is included in our climate change scenarios that we then apply to the crop models. What we do for the things like groundwater is trickier, it's hard, and we're working on bringing that up, but in terms of surface water irrigation sources, what we do is we team up with the water MIP crew, and then we overlay the results. We look at the results separately, and then we overlay the results, because you're absolutely right. If we just assume that we're going to have water to put on for irrigation of the crops, we're not getting the right answer. So we do then, and in several studies, we did that even at the very beginning in the first national assessment. We looked at what were the projections, the hydrological projections, in terms of water availability for irrigation. And that's what we're doing. We also do that at the global scale. Joshua Elliott has a paper on that in PNAS. It uses the results that I showed, and then it combines them with the water availability results. That's also a really great question.
But my question is, what is the bigger constraint? Is it the hydrological aspects or temperature? And why do people always talk about temperature as the criterion and not hydrological?
Yes, that is also huge debate. Now, there's a group of statistical-based modelers, really coming from the economic side, who they don't do just so much projective modeling the way we do, dynamic process. They do statistical modeling, and they feel that when they do their statistical models of observed relationships between temperature, precipitation, and yield, that they're getting better results with temperature. I think, but basically, anybody who has ever grown a garden, right, knows that we have to look at both, and that precipitation is absolutely critical for crops, just as we heard from the last query. I think that there's something very subtle going on with people who are looking at the empirical data, because with high temperatures, one of the main effects is that the crops run through their growth stages faster. And so the growing season becomes shorter. And I think I have a hypothesis that the reason why they're pushing temperature is that it's because it's a shorter period, and so and temperatures continue, so they have all the data, whereas precipitation is much more spotty, and then you're not getting as much of it. You just don't have a long enough time series in your empirical relationships. That's what I think. But it is a huge debate. Temperature is very important, because that that growth stage effect, plus high temperature effects on critical growth stages. For example, if there is a heat wave during corn pollination, and basically the corn, the corn is grown like, in factories in the fields now, and they all pollinate at the same time. If you get a heat wave during that pollination, it can literally cook the proteins. So you have numerous effects of the high temperature. That being said, I am firmly I don't think we should choose. I firmly think we need to understand the temperature effects and the water and precipitation effects. And that's what our type of modeling really, because we can understand the processes involved. But it is definitely a debate.
That's a good way to end. So let's thank Cynthia one more time.
Thank you.